This is my homemade quantum computer. It's totally useless because of how small it is, but technically it is a quantum computer. I made this because despite doing my whole PhD on quantum computing, I'd never actually seen one in real life before, and all the pictures I'd see were of these crazy space age looking contraptions. But quantum computers aren't at their core actually that complicated. So I figured I'd try and explain them to you while I work out how to actually make one. I had some ideas going into this, as well as an unhealthily large collection of crystals and lasers, so I figured, how hard could this be? In theory, a quantum computer is pretty simple. In the first part, you have these things called qubits. And in this case, I'm going to be using light to be making my qubits. There's many other choices you can make, but light is by far the easiest thing that you can do at home. Usually, for a good quantum computer, you would have a whole bunch of qubits, like at least 20 to be respectable. For me, though, I'm just going to have the one because it's going to make the whole thing just way, way easier to do. But that's why this quantum computer is going to be, while technically a quantum computer, pretty useless. In this first step, we want to guarantee that the light that's going to be exiting the step is in a particular state. So what I mean is there are lots of different states that light could be in when it comes out of this laser. But we're going to put in this little filter here that is going to filter out all of the different types except one. And so that guarantees that the light that is coming in here is of a particular state. And we know what that state is. But what's going to happen in the computation step is that that light state is going to change. And the way we're going to do it is by using this calcite. Depending on what computation I want to do, I can change the thickness of the calcite. I can also change the orientation, and I could even add in some other ones that are also at different orientations. In a quantum computer with more than one qubit, you would actually need some more fancy crystals than the ones that I can afford. For example, one called BBO. What would happen in that case is that the two qubits would enter and exit, but the light that comes out afterwards is in a particular state called entangled. So these two qubits are now entangled with each other. But we're not going to have to worry about that because frankly, I can't afford BBO crystals. And also, even if I could, they're super, super hard to work with. So we'll stick with calcite. All right, so our light starts off in a state that we know, then it goes through this computation step and gets changed in some way. And the final step is really simple. We're going to try and figure out something about how the light's changed. We won't be able to figure out exactly what it's doing now, but we will be able to figure out at least some hopefully useful information about the light. At a high level, that's all a quantum computer is. But you might be wondering, how is this like a computer at all? Well, computers also just take inputs in the form of zeros and ones, and then they transform them in some way. For example, imagine a computer program that helps you add. You put in two numbers, which it'll interpret as zeros and ones, and then it'll start processing those in like the standard algorithm for adding. Like, first step, add the rightmost numbers. Second step, add the next two numbers, and if there's an overflow, put that into the next column, etc. Then the new set of process bits is the answer. In a similar way, quantum computers take some qubits of light in some state and then process them to give you some new state. A quantum algorithm might look like, first put this crystal at this angle, then put in another fancy crystal, and then whatever you get out at the end is the answer you were looking for. But going back to our standard computer, you can do a lot more than just add numbers. You could, for example, multiply numbers, or, render an image of an oscillating electron, or really whatever you want. And in the same way, a quantum computer is something where you can do a bunch of different processing of light, depending on exactly what it is you want to compute. We'll get back to the question of what quantum computers are actually computing in the next video, but for now, our aim is just to show that this setup can transform light in lots of different ways, because that's what a quantum computer is. So that's what's going on here at a high level, but let's get into the details, starting with what is a qubit exactly? Here's everything that you need to know about light to be able to make a qubit from it. Light's whole thing is to harass charged particles, like this electron. So this is what I mean. Imagine we've got some light coming along. I've represented it like this because as the light passes by this electron, these little things are supposed to represent the force that the electron will feel because of this light. So you can see that this light is first pushing this electron up, and then down, and then up and down. So as the light goes past, the electron will jiggle perpendicular to the direction of the light. But we live in 3D space, and so that leaves the light with lots of different options in terms of harassing this poor electron. So one option is that the light is oriented like this, which means that the electron will jiggle up and down as the light goes past. But we can orient the light anyway. So it could be like this, which means that the electron will be jiggling forwards and backwards. But it can be any other direction as well. So if I put the electron here and the light is coming towards, that's directed like this, we'll call that horizontally polarized light, whereas light that is oriented like this is called vertically polarized light, and you can have every option in between. So if the light was like this, we could write the state of the light like that. All right, so if I have some light and it is in a particular state, so say this state, then this is a qubit. Now you might be wondering, what has this got to do with a bit? A bit has like just two possible states that it can be in. It can either be in the 0 state or it can be in the 1 state, whereas this thing has an infinite number of states. So where's the like two-ness in this? Well, there actually is a two-ness in this state. And that is that if I take two of these, and let's say this one is oriented horizontally and this one is oriented vertically, and I combine them, I can actually make any other type of light that I want. Here are two laser pointers, and this one only gives out horizontally polarized light. This one only gives out vertically polarized light. And my claim is that by combining these two lasers, you can actually get any other qubit that you want. But it just depends on how you combine them. So for example, which one is stronger, but also how in sync or out of sync these two lasers are. If you think of the horizontal state as the 0 state of light and vertical as the 1 state, then you can see what people mean when they say that a qubit is both 0 and 1 at the same time. No matter what type of light you have, you can always think of it being made of some 0 part and a 1 part. But the light might be more horizontal or more vertical, in which case it's more 0 or more 1. But the important thing to remember is that any light state can be made by adding 0 and 1. Now that's really not obvious, so I'll try and prove it. Say that the light that you really want is this kind of 45-degree light. So that's light that originally pushes in this direction and then eventually will push in that direction. How can I get that? By just combining the two bits of light that I do have, which are oriented like this and this. Well, here's what would happen if I just shone some horizontally polarized light at the same time as some vertically polarized light. At first, this one is pushing in this direction, and this one is pushing upwards. So in total, it's like this electron's getting pushed up and to the right, which is exactly what we wanted this light to do. So you can see that shining these two things at the same time just gives you light in the 45-degree polarization. That's not going to be quite right, because if you just shone these two bits of light, then you're going to get something that's a bit too strong, even if it is in the right direction. So you kind of need to tone both of them down. And these two factors just represent how much you're going to tone down both of them. You got to do a little bit of trigonometry to figure out that those are the right numbers, but it's not a really big deal. The point is just combining horizontal and vertical light got you the light at 45 degrees, which is what you wanted. But say instead you want your qubit to be in another state. So for example, more like this. And you can see that this is mostly upwards, but a little bit to the right. So to actually do this, all you got to do is combine these two lights as before, but make the horizontal bit of light way less strong. So in other words, like literally turn down how strong the light is that's coming in the horizontal direction. And so now the electron will be pushed very weakly to the right, but much more strongly upwards. And so in total, it's going to be pushed in this direction, which is exactly what we wanted. So in other words, this has to be a small number and this has got to be a bigger number. Okay, so that works, but here's a way more tricky one. What if the qubit that I want is light going in this direction? Now what I want is light that is going still in the right direction at first, but instead of pushing up, it actually pushes downwards. Is that possible? Well, it is, because if these are my two light beams, so far I've been considering the case where both of them start off at their sort of maximum strength. But what about if I start off the horizontal component at its maximum strength as before, instead of starting this one off so that it is pushing upwards with its maximum strength? What if I start it so that it's pushing downward? Now I got exactly what I wanted. This light is going to be pushing to the right. This one is going to be pushing downwards. So the total effect is like you're pushing in that direction. Because we had to flip this light sort of upside down, the way that we're going to represent it in the equation is to represent this as a negative. There's another way to think about this same state of light that's going to be really useful later on in the video. So let's start with this horizontal and vertical light as before, but now we're going to start with them being perfectly in sync with each other. So now when this is pushing upwards, that is pushing to the right, which isn't what we wanted. So how do we get the type of light that we want, which is the one that pushes to the right at the same time that it pushes downwards? Well, why don't we just move these two bits of light out of sync with each other until they're here? So now they're kind of perfectly out of sync with each other. And you can see that this light is pushing down when this one pushes to the right, which is exactly what we wanted. So another way of thinking about light is it's not just about how much horizontal and vertical there is, it's also about how in sync or out of sync they are. Okay, so I hope that gave you the gist of why you can get any polarization of light you want, so any qubit that you want, by just combining light that is in this state and this state. And by adjusting A and B, which is both the relative strength of these two lasers, but also how in sync or out of sync these two lasers are. So this is your qubit. The horizontal state is kind of like the 0 state, and the vertical state is like the 1. But you might be wondering, like, how is this actually like a bit? Because bits contain information. Where's the information in this? Well, there is information, because if I have a bit of light that's in a particular state, and I don't tell you what that state is, then you don't know what A and B are. But if you find out later what that state is, then you do know A and B and you've learned something. And so that's the kind of way that information is encoded in a qubit. But you can see that it's like a lot more information than what would be inside of a bit, because to find out what a bit is, you just need to know, is it 0 or is it 1? Whereas there are so many more options for what A and B can be. And so in a way, a qubit really contains a lot more information than a bit. It's another question whether you can get that information out, but for sure there is more information encoded in there. The first step in any quantum computation is to start your qubits off in the state you want them to be in. So far, I've been saying that the way to do that is by combining this horizontal light and this vertical light in exactly the right way. But that's actually a really, really difficult way to do it. And it's not going to be the way that we're going to do it at all, because it's really hard to determine how in sync or out of sync these lasers are. Like, I'd have to start them at exactly the right time for them to be in sync, and that's just basically impossible. So the way that we're going to do it is instead using this piece of plastic. These bits of plastic are called polarizing film, and they don't look like much, but look what happens when I do this. If I put it like this, and then I slowly rotate it, you can see it gets darker and darker till it gets to its maximum darkness, and then gets lighter and lighter again. You may have seen these things in science class. I certainly had, but it was only when I was researching this video that I understood how it works, and it's super clever. So essentially, this is made out of long plastic polymer molecules that are all aligned with each other. There's a whole bunch of them in here, and they're all facing in the same direction. This has a really interesting effect on light because it acts as a filter for certain polarizations. I'll show you how. Let's represent one of the polymers in the material like this, and it's going to have a bunch of electrons in it. By the way, the reason why we're always talking about electrons is that electrons are generally a lot more free than protons are. Protons are heavier and they're bound up in the nucleus, and so they just aren't that likely to move around, whereas electrons, especially like these outer shell electrons, can be quite mobile. And so that's why when we're talking about what happens when an electric field passes through a material, it's more useful to talk about what happens to the electrons. Let's say I have this electron, and indeed a bit of light comes and hits the electron. Now, if the light is oriented in this direction, then what happens is the electron feels a force up and down. And because it's pretty mobile, it has a long bit of molecule that it can move up and down in. But that means that as this light comes and hits this material, it makes all the electrons in here jiggle quite a bit. And all of that long distance movement means that the light's energy gets wasted. And so the energy of this light just gets used up before it goes through. And that's why you don't get light that is of this polarization go through that material. On the other hand, what would happen if the light is perpendicular to the direction of the molecules? Well, in this case, the electron wants to be able to move in this direction, but it can't really. It's sort of stuck. Like the molecule isn't that big on that direction. And so it doesn't really move at all. And that means that this energy from the light coming in on this direction doesn't really go to the electrons. They don't really do anything with it. And so it's able to pass right through. And so that's why this simple bit of plastic is able to filter light that's coming in this direction and pass through light that's coming in this direction. But what about light that's oriented in some other direction? Well, for light coming in like this, remember, it's the same as if we had a bit of horizontal light plus a little bit of vertical light. And so we know exactly what's going to happen. The vertical part, which is this part, is going to get used up. The electron is going to use that to jiggle up and down, and so that bit will just get wiped away. The bit remaining will be the horizontal part of the original light because the electron can't use that, and so it just stays. But you can see this A demonstrates that the light has gotten weaker. So if you originally had light that was very, very close to vertical, then most of it will be cut out. Whereas if you have light that's pretty close to horizontal, then most of it will go through. So no matter what type of light we had coming in, we know that afterwards, as it goes through, it's all going to be horizontally polarized in this case. Or if I turn the filter around, now it filters all of the horizontal light, and so we can guarantee that the light is going to be vertical. All right, so that's how you make your state. You get a laser, you put a filter on it, and now you can guarantee that the light is in the state you wanted it to be in, because only one type of light can go through the filter. The next bit that we use the filter for is the measurement. And that's because as you put this filter in front of the light, it will cut out some of the light. Remember that all the light that gets through to the measurement stage is going to be a combination of horizontal and vertical light. And this filter is going to cut out all of that horizontal component and just leave behind the vertical component. So if we look at the percentage drop in the brightness, we know how much of the light that got through the computation step was in the vertical direction. What we're not going to be able to know from this measurement, though, is how the vertical and horizontal components were aligned with each other. Were they very in sync? Were they very out of sync? We don't know. This measurement will tell us absolutely nothing about that. But it will tell us just at least how strong those two components were. It's finally time to understand the computation section and what exactly this calcite is doing. So check this out. You can see that this calcite splits this line into two lines, one to the left and one to the right. But what's really interesting about how the calcite does it is that it splits the light according to its polarization. So if I go like this, it filters out just the one on the left, and if I instead change it to filter the other polarization, you can see that it just filters out the one that's on the right. So that means that these two lines are light with different polarizations. Here, what I've done is start the light with the filter at 45 degrees. But remember, light that's oscillating at this angle is just an equal combination of horizontal and vertical light that are in sync. That's exactly why it's a good idea to start the quantum computer in this state, because both the 0 and the 1 are there at the same time, and that's usually when something interesting starts to happen. If I put this calcite into a laser beam, it splits it into two different polarizations, and you can see that by putting this filter in. If I put this to the right angle, the hell? I hate doing experiments. Oh wait, nah, it worked. Okay, this is the right angle. That cuts out one of them. So that means the other one should be 90 degrees from that. Yeah, that worked. Okay, sorry, I take back what I said. This calcite will split any incoming light into two different polarizations, and exactly what those two polarizations are will depend on how you orient the calcite. So if I orient the calcite just right, then that means that the light that's coming in will be split into horizontal and vertical light. I went online and I looked up ways that you could make a quantum computer using birefringent crystals like calcite. And it was really clever how they worked. I would definitely not have come up with it. And so I'm going to try and explain that by first understanding exactly what it is that calcite does. Calcite is a birefringent material. That means that it treats the two different types of light very differently. For example, if the calcite is oriented a particular way, it might let horizontal light pass through fairly quickly, but slow down vertical light a lot more. Which is strange. I mean, why does light even slow down in a medium in the first place? If you want to know why, well, that was a whole other video I did. And the answer basically boils down to, I have no idea, stop asking me. Anyway, remember that if we want this thing that we're making to be a quantum computer, it needs to be able to transform the input light. There are two things that you can transform about the light that's coming in. One is how much horizontal versus vertical light there is, but the other is just how in sync or out of sync those two components are. Our calcite computer is actually just going to change how in sync or out of sync these two are. And it's actually kind of perfect for doing that, right? Because it slows down the vertical component more than the horizontal component. And so once these two bits have gone through the calcite, there is naturally a lag between the two. That's actually why the light splits up when it hits the calcite in the first place. Because as you might remember, the slower that light goes in a medium, the more it bends. And so the one that gets bent more is the one that is going slower through that material. And so then these two things split away from each other. But that has actually gone from a feature to a bug now. We want this lag between the two bits of light, but we don't want it to be that the horizontal and vertical split away from each other too much. Instead, we want them to still be pretty much overlapping with each other, because that's when the two bits of light can interfere with each other. We're going to try and get around it by having an incredibly thin slice of calcite. So something like this will not do at all because the light can split very appreciably in that distance. What we need is a slice of calcite that is just thin enough to introduce a little bit of lag between these two, but not too thick that the beams really split from each other very much. Is that possible? Is it possible to cut something like this so thin but so precisely? Apparently, I saw it online for a lot of money, much, much, much more than I was willing to spend. But there is a cheaper alternative than doing it with calcite. This sort of stuff makes me so nervous because it's all so precise and I don't want to mess it up. All right, here we go. Look at this marvel of engineering. It doesn't look like much, but this is precisely the right kind of material with the exact right thickness such that if I place it in the beam, then what is going to happen is these two bits of light have gotten slightly out of sync with each other, but the thickness is still small enough that the two beams haven't diverged very much. And you can see that that's true because there's only one dot there. And so this here is it. This is the quantum computer. This is really cool for me because I literally just opened this, and so this is the first time I've actually seen this quantum computer work. All right, let me just play around with this a little bit. Oh, it's so exciting. That is so cool. See, if I put it at this angle, it exactly cuts out. I have no idea how it's this good. This half-wave plate is made for a specific wavelength of laser, which this is not. But even so, it's pretty much giving me the right result. That is really surprising. I didn't expect it to be this good, to be honest. I guess that actually means that I can use this quantum computer to really do a calculation. I, I kind of didn't think I would be able to. Like, I thought that, technically it would do a computation, but noisily and badly enough that it wouldn't really be useful for anything. But now I think I can actually do a real computation and show you it and like get the right result even. That's cool. All right. Well, I guess that's going to be the next video then. Bye.